One more problem. Section 9.2, number 38. I assigned 36, which is similar. Now, in this problem, we still have that the t is in this range. It'll always be in this range. Okay, I'm never going to switch that up on you, so don't worry about that. But we want to solve sine of 2t equals cosine t. Okay. Now, this is a case where using the method where we set theta psi equal to 2t and then kind of did a bunch of n's and stuff, that method is not super useful here. It might work, probably will work, but I think it takes a little longer than the quicker version. So let's think about the double angle identity here. Now, earlier we had done a problem where we could have used the double angle identity, but it would have led to something we couldn't have used the zero product property on. In this case, that will not be a problem. Okay, so use the double angle. This is double angle. So double angle identity tells you that this is equal to 2 cosine t times sine t, and that needs to be equal to cosine t. Now, you may be tempted to divide both sides by cosine t, but if cosine t was 0, you couldn't do that. So it's universally better in algebra to bring the everything to the left, or to the right if you prefer. I like going to the left, and then factoring. Now, we had done this in a previous problem, and it ended up that one of the two factors did not have a solution. But, you know, if you can't know whether it does or doesn't unless you check. So, in this case, we get this solution. We factor the cosine out. We're left with 2 sine t minus 1 is 0. So now we can apply the zero product property and say that this is cosine t equals 0, or it is 2 sine t minus 1 equals 0. And these two equations are solved in the usual way. So if I want to solve the first one, cosine t equals 0, well, I'm looking at a unit circle, and I'm looking at places where the cosine, or the x value, is 0. That means I'm having no horizontal movement away from the origin. Well, that's these two positions here. And this one has coordinates 0, 1. It corresponds to the angle pi over 2. And this one has coordinates 0, negative 1. And it corresponds to the angle 3 pi over 2. Now, we can't write negative pi over 2 to be useful in this problem because of that restriction. But for other purposes, you could say negative pi over 2. Like if you're dealing with an arc sine, for example. But we're doing with this. So again, you can solve this with an inverse cosine function, but you're only going to arrive at that solution. Inverse cosine only gives you stuff in quadrant 2. So the unit circle method is the way you're going to have to do it to get all the solutions. Unless you start memorizing rules about how you take inverse trig solutions and getting other solutions. And I think that's a nightmarish thing to want to try to do. So we get two solutions there. We do the same for the other problem. Okay, so the other problem is this 2 sine t, drop my pen, 2 sine t minus 1 equals 0. So I'm going to first solve for sine t. How am I going to do that? I'm going to add the 1, and then I'm going to divide by 2, and it gives me 1/2. So I'm asking the question, which angles in the interval in one rotation give me a sine value, a y value of 1/2? Well, that's going to be here and here, right? Because this thing has coordinates root 3 over 2, 1/2. Its sine, the second coordinate, is 1/2, and that's pi over 6. And the other one is over here. Its coordinates are negative root 3 over 2, positive 1/2. Again, the sine is the second coordinate, and it's at 5 pi over 6. So I get 5 pi over 6, and I get pi over 6. And these four solutions together are the solutions of this original equation within that interval.